And right now, let me introduce you our first speaker. And our first speaker is Adam Badura. Adam Badura will have a speech about the spaceship operator and the operator universe. Adam is a technical leader at Nokia. He has over 10 years of work experience. However, his passion for programming, with C++ mostly, is much older. Adam's interests are mostly the development of good software across all levels, from general design to technical details of specific implementation. His natural bent for formal things is complemented by his eagerness to share his own experience and learn from the experience of others. Adam Badura, go on the stage and start your lecture. Thank you. Doesn't, okay, it works.
Okay, so welcome to my presentation, and well, let's start. What are we going to talk about? Firstly, I will cover what C++20 changes for operator overload. There are some not big changes, but quite useful. Then I'm going to take the main course, which is the spaceship operator and its issues. Note, though, that I'm not going to describe the spaceship operator in detail. I presume this is already known. There are presentations about that topic. And then for those who are still not there, there are a few tips of how to deal with this when you are not still in the C++20. But first, maybe a personal reference. Not 3,000 years ago, but 13 years ago, on the then functioning Complang C++ moderated news group, I think it's that now, I have written a post, generic compare function, and I have suggested that we should have such a function that would return a negative value and so on. You know what to expect from the spaceship operator, right? The reception was mixed. There were some people claiming that, well, I can see why do you need it, or I wonder if you have it thought it through. But then there were also some positive votes, like yes, it would be nice and potentially efficient, something like. And here you show, you can see what ended up being the spaceship operator. Back then, it wasn't clear yet, though. So this played out nicely. But, well, 13 years passed, and we are now into C++20 operator overload changes. I think the most useful thing is that from now on, the equality implies inequality. If the compiler sees the expression that A equals to B, then first of all, it will try to match it directly, like A equals to B, but also it will try to revert the direction and match B equals to A. And on the other hand, when it matches when it sees the inequality operator, it will, of course, try to find the inequality operator definition, but it will also try to use the equality operator in both directions. So now, when we write equality operator for class B, then we can class B has an equality operator to class A, and we can use inequality and even revert the order and compare A to B instead of B to A, and it will still work, just as we would expect. This is particularly useful for the cases where one of the classes is not in our code base, so we cannot supply appropriate operator. And note that now it also means that we can safely use members. Overload the operators as members, not as friends or free functions, because we no longer have to care about the order of arguments, right? Because the compiler will try to match in both directions. But you might notice that there are some missing candidates. The compiler will not try the red ones, and it has practical implications. This code will not compile. While we have inequality for B, when we reverse the order, the compiler will not try to match, because with an inequality, as I have shown here, it tries directly the order stated in the source code, or it will immediately jump to equality operator. So this will not compile, and it might be surprising to someone, because after all, we just reversed the order of the arguments, right? But I think it's not a practical problem, because let me be honest, this is somewhat pathological code. Who would define just the operator inequality and do not define equality operator? In many years of my practice, I didn't met such case in the code. It's often the other way around. People define equality and skip the inequality, and well, for good, because now they no longer have to define it, because it will be implied by the equality. So, to sum up this part, no boilerplate code for operator inequality. Previously, we had to define it as exactly as it was stated here, right? So that it's not equality. We no longer have to write it, because the compiler will do it for us. And we no longer have the dilemma between implementing the operator as a method or as a free function. Method is now just fine. It no longer has the disadvantage of treating the left argument specially, because it's the self. Now it's symmetrical. I will get back to this topic later on as well. But what about relational operators, other than equality and inequality? We might imagine that perhaps in a perfect world, this could be deduced, this could be deduced, this could be deduced, and eventually all operators would come down to inequality operator, the less than operator, right? And perhaps with a negation if needed. This would allow us to write just one operator, the less than operator, and have the rest there. But it's not there. The spaceship operator provides for this, but there are no special rules to rewrite the source code to use a different operator than the one stated, other than the spaceship operator, of course. Okay, teraz lepiej. Oh. The spaceship operator and its issues. So let's start as a reference point, because we will be returning to this point class many times. We have a point class with two members, x and y, of course, and the spaceship operator is there. It's defaulted, so it will be done member-wise. First x will be compared, then y will be compared. As you can see, the code on the picture, of course, compiles. You can see that the test function uses less than operator, and it works because the compiler knows what to do with the spaceship operator, how to calculate the result. You can also notice that the const expression version works as well. It's const x by default, if possible. As usual, the same applied to constructors, for example. So we can use it in static assert on the last line. The important part is that the operator should return auto, and you must include the compare header for this to work. But the compiler is generating errors or warnings on that, so no problem. But what about the performance of this operator? And I found out that it's lacking. I provided a better implementation for some types. C++20 introduced the bit header, and in that header we have, for example, bitcast. It's also known to as a concept known as type tuning. I'm not going to get into details. You can find presentations about that. In essence, for the simplest types, pod types, it just reinterprets the memory using a different type, but in the scope where it's safe. Unlike with reinterpret cast, which could do it for every type, but in many times land up in the undefined behavior. Bitcast does not have this problem, but it's also limited to which types it applies. For example, it requires, of course, that both target and source types are of the same size. So here we are able to convert the point type to just uint32, because those are two words, right? So it's a double word. This is valid. It's not generating undefined behavior. And when we reinterpret the points as 32 integers, we can compare the integers directly. We no longer have to iterate over the members. And looking at how it looks in the generated assembly code, we can already guess that it will be a better implementation. Notice that with the default, we can see the traces of what we would expect. There is a jump because the compiler first compares X, then it compares Y. And with bitcast, it doesn't. There is no jump in the code. So it not only it's shorter, there is also no jump. So we would expect it should be better. And it indeed is better. If we benchmark the code, the version with the bitcast is twice as fast as the defaulted version. Now you will notice this red for big endian. This code, I have cleverly chosen here the points which do not show a bug under little endian architectures. If you would do the same under little endian architecture, it would not work because the bytes are in a different order. And so let's try not to cheat this time. Again, approach the problem in a generic form. With the C++23, we will get in the same header, the bit header, a byte swap function, which swaps bytes of simple integers. Pretty useful. But before that, and for the sake of this presentation and the tests I have been doing, we use the byte swap implemented manually only for the 32-bit integer. It's pretty obvious from the implementation what it does. Anyway, I was playing around with this, and it seems the compiler ends up generating the same assembly for both versions, so it's pretty optimized. So now we use another feature from the C++20. It's the endianness. It's also defined in the very useful bit header. We can now simply check and most importantly, portably check what is the endianness of our machine by comparing the smart enumeration type, the native value to either little or big. So if we are little endianness, we need to swap the bytes first so that the comparison is correct. And if we do that, the assembly is no longer that short, of course. You can see the byte swap instruction. It also shows up if you use the built-in byte swap. But it's still better than the default separator. It's not so good. It's we were doing half of the time used by default, no longer. Now it's significantly more. However, it's still better, even in the worst case. So we are on the little endian machine. If we would be doing the test on the big endian machine, the const exp if doesn't trigger, we do not swap the bytes, and we are on the happy path. So twice faster than the default. But this made me think about another idea, because the byte swapping is the problem. Because of the NDNS, we have to swap the bytes. And while it might be needed in a very general case of any arbitrary pod structures, our point is much more restricted. We know that we have only 2 members and they are both integers. So we can just compute the final integer by first shifting the x part so that it is the larger part, and then adding the y part. And if we do this approach, then we no longer have the issue of swapping the bytes. This will work with both versions, both NDNSs. And the generated code is still not as good as was the initial one for the big endian architecture, but you can notice that it doesn't contain any jump. So it is promising, and in fact, indeed, if we count it, the numbers approach, where we treat the members, we sum them up to a specially calculated number, it's almost as good as it was with the big endian version. So we regained everything we lost, and we are still half the performance, even better somewhat than the default one. However, this is even less general, because it not only doesn't apply to all pods, but also the pod have to be consist of numbers, so and be small enough so that we can squeeze them into a single number in this way. Now, with all these, one could think, what about memcompare? Because maybe we are trying to solve the problem that's already solved. After all, we notice that in the end we are just comparing memory, right? And this also should address the problem of NDNS, because the X is before the Y member. But that's a dead end. Memcopy is tragically slow, even compared to the default implementation. I have dived into the code somewhat. It seems to me that the main reason, I'm not showing here the assembly to save some time, but the main reason is that the memcopy version, although it's quite simple, it does call the memcopy function, and this call to the standard library is killing the performance here, I presume, because that's the only difference I can see. But maybe that's something else. That's my assumption. When I was giving this talk on an earlier local meetup, for some reason, under the tests with the quick C++ benchmark, the compiler eliminated the memcompare call. It was showing in the compiler explorer in the assembly, but the quick benchmark eliminated it. And then the performance of the memcompare version was on par with the default one. But I wasn't able to reproduce what circumstances lead the compiler to eliminate it. I think I was doing the test in exactly the same scenario yesterday, just to be sure that the results are on top. And not because I was making slides at the night before. And the compiler did not eliminate the call. So as usual with the performance, it's a kind of game with the compiler. With a more complex code, you may never be sure what the compiler will end up generating. So the conclusions so far. Member-wise comparison may be suboptimal for pod types, right? Because it requires how it's implemented means that you will end up in generating many if statements because of all the members, and this is what the default currently does. I emphasize currently because that's not what it could be. It seems that compiler should be able to do the same, right? First of all, let me also emphasize that this is not the problem inherent to only to the spaceship operator and the default version of it. If you would write the same code manually by hand, and you would probably do so for pod types, you would end up with exactly the same. The problem with the spaceship operator is that when you are writing it on your own, you are much more likely to do something more clever than just member by member compare them all. And if you have the option to just default the operator, it's so tempting, right? You don't have to write this code by hand. And if the compiler doesn't optimize it either, and currently it doesn't, then you end up with something that's suboptimal. Maybe it's not a problem in your domain, in your program, and having it default is just simpler and shorter. But maybe you are on the edge of performance, and it is important for you. So keep it in mind. And now some traps, because now let's consider the case that we indeed implemented the operator on our own, either because there is something more complicated than just do it member-wise, or maybe because we want to squeeze the performance out of it. So we implemented it ourselves without defaulting it. And what happens? We no longer have the equality. If the spaceship operator is user-defined, not defaulted, then it no longer implies the equality, or inequality, of course, because it's the same now with C++20. So in this, if you would open this example, it would not compile. The spaceship operator is not defaulted, hence the equality breaks on the compilation. So we could think that perhaps if we add the default to the operator, equality operator, then we are okay now, right? For sure it compiles. It will even pass all your unit tests because it does what you expect. It will compare member-wise. But if you disassemble the code, you will notice the same pattern we already saw. It indeed does it member-wise. The default here doesn't mean that it will use the spaceship operator. It means that it will do the equality member-wise, ignoring your spaceship operator. Which means that this version is suboptimal. If you took care of implementing the spaceship operator to squeeze the performance, and then forget to implement the equality operator or default it, well, if you forget and if you use it, then you will get a compiler error. But then you go to default it, assuming that it will work. It will indeed work in the sense that it will do the same comparison we implemented manually, but it will do it in the not optimized, unoptimized way. And you will not find it out unless you have performance tests to cover it, because functionally it will do the same still. It will still do compare it in the same order. So, conclusions for this. The equality operator can sometimes be faster than the general spaceship operator, because answering the question, are those two objects equal or not, is a simpler question than answering what order they are in, because the classic case is the short-circuiting on container size. Like if I know that I am comparing two containers and they have a different size, I already know that they are not for sure equal. I might not know which order they should be because this depends on the members under indexes, but for sure they are not equal. So I can easily answer this question, and it will take arbitrarily long time to answer the other question because I will have to just go through the containers, which might be very long. So it is reasonable to implement the equality operator separately in such cases. However, sometimes it's not, and this is the case we are covering here in this presentation. The pod-like simplification or summing up the members to a number to compare to just have a single comparison. In those cases, the equality is just as performant as the spaceship operator. And yet we pay the price for the decision that was made to secure the performance. And it's interesting, if you go through the documents that led to how it looks now in the standard, you will notice that the argumentation they used to defend how it's now specified works exactly opposite in our case. The claim there was that if you default the operator, if the equality operator is defaulted and uses the spaceship operator, it will be less than, it will be suboptimal. User might naturally assume that it will be good, but it will not be good because it will not do the optimized way. And it works exactly the same now. When the case is that the spaceship operator is user provided, not defaulted, then defaulting the equality operator leads to suboptimal code. So either way, we are not fine. Either way, one of the cases will be misleadingly suboptimal. And so the use of default on the equality operator when you have a custom spaceship may be misleading because it will do something else than you might think it will. And if it happens to imply the same order, or it happens to imply the same order in the unit test you did for a quality operator, how many unit tests you did do for it, then you may leak a bug, either a performance or even a functional, if they are not indeed the same. And so, while I'm not claiming here the committee did a bad choice, if you really go through those papers, this was, I think it was a trade-off between two evils, and they chose the lesser evil. And so I guess it was a right decision, but it nonetheless was a choice between two evils. And if you are now on this particular case where you have a custom spaceship operator, then you have to remember that you should probably implement the equality as well, and probably, if it applies to you, by doing exactly the same thing as the spaceship operator. Perhaps you can call it explicitly. To be honest, I didn't check this. I would expect you could call it explicitly in the equality operator, not to duplicate the code itself, only the call. So, yeah, with the custom spaceship, we need to provide a custom equality, even if it would be the same. Now, some operator press C++20, I lost part of the title. It's press C++20 operator overload tips. Who is still not using C++20 in their work? Quite many, and this aligns with the JetBrains annual survey from 2022. I checked it. Only 23% of people reported they are using C++20. If you go by those numbers, you will notice they do not sum up to 100%. I presume that some people use many different versions and they checked many different boxes. And that's why it doesn't sum up to 100%, but more. Yeah, so it's a growing trend, as you can see, but it's still far from even the half, not to say majority. So most of us still must leave before C++20, and what can we do then? First, what's your favorite way of overloading? A free function, a friend function within the type, or a method? I have seen, of course, all of them. If you implement by a free function, it's pretty obvious, right? You have a free function in the same namespace. If you implement by a friend, you define the friend in the type. It has the advantage that it works nicely with ADL, nicer than the free function. And the method is the last one. Some people don't like the friend, rightly. This is a good use of friend, but it may trigger someone who just sees friend and goes red. So the method is then an obvious alternative because it also grants you the access to the members, but doesn't have the red word friend. How they compare? Does the generated code differ between the three versions? No, it doesn't. Well, of course, this is a bold statement because in the end, it's the compiler choice what to generate, but I didn't manage to make it generate something else. It will always ended up with optimizations, of course, turned on, it generates the same code in all 3 versions. Then what else differs? Compilation time differs. The free function compiles much slower, as you can see. Friend and method are way faster. And this is, in my opinion, a pretty important factor. Some people will also notice that if you use the free function approach, then if you miss the operator, you call it with the wrong arguments, and you have many types with many operators, the compiler might end up producing huge compiler error listing all the operators it tried to match and why it didn't match, because all of them are available. And this makes the error message pretty unclear. And the friend and method don't have this problem. And this also already hints why they don't have this problem, because friend and method approach is found on a much earlier stage. And the compiler doesn't see so many possibilities at that stage, and hence it also finds determines what the operator is there much quicker. So from the compilation time point of view, I would suggest either friend or method and drop the free function approach if you can, of course, because if you have to deal with you provide operator for types you do not control, why would you? But if you do, then you of course cannot inject anything into them, which is required by friend and method approach. And the features supported differ. I already hinted on that. Free function and friend functions have access to private members. I marked it as not okay. That's, in my opinion, that's disadvantage. In general, you would expect that the equality in relations should refer to members you can observe. And if you can observe them, then you do not need private access to them, right? While that's a perfect world scenario, in practice, being able to observe, or at least hypothetically, might not be feasible for the generated code. So the access to direct private members may just lead to better code, even if conceptually you could use public accessors or other inferred knowledge about the type. But as a rule of thumb, if with everything else equal, it's better not to have the access than to have it, right? If you don't need it. So the symmetry on arguments. The free function and the friend function, they are symmetrical on arguments. I mean, you can define a version if you compare 2 different types. You can, and if it applies to your operator, you can define another overload that switches the types. And then whether you write A equals B or B equals A, it's all okay, as you would expect. Whereas this is not possible before C++20, notice, with method, because the method treats the first argument especially. It's the self object, right? So to ensure that the reversed operator is supported as well, you would have to inject it into the other type, which is fine if you control it. But if it's a standard type like a string, for example, you compare with a string, then you cannot inject operator there. So symmetry is in general not fine with method approach. And the last one is the unexpected use cases. There the free and friend apply. They fail this case. This is the consequence of the symmetry. Because of the symmetry, if you have in conversion operators in play, you may end up in using the operator for 2 types you never intended to use, but only because they happened to convert to the types that you listed. And it's fine if it's on one of the arguments, then you would probably expect that it will work. But if it's done on both arguments, then it means that you are executing your operator for something you didn't intend. And I didn't hit this problem in practice, but in theory it's possible. I didn't hit it in practice because in general you should avoid implicit conversions, and then you don't hit this problem. But it exists, there is this issue. Another tip for pre-C++20 is to, of course, implement with the exact logic only the equality and less than. The inequality is then implied by equality, and the other relation operators the same. Exactly as we have discussed in the beginning of the presentation, right? With this approach, all the 4 functions here are, this is just a boilerplate code. You have to enter it to make it work, multiplied by all the types and the symmetry you need. But the implementation is implied. There is no logic here. The only logic is in the equality and less than operator. There is the only place where you do actual implementation for your type. That's specific for your type, and the rest is should be implied. Now, one could wonder if we should not deal with the less than or equal operator to skip the negation. It would require comprehensive tests, but I think that's not worth the case. That it is not worth, because the generated assembly within the assembly itself should be able to deal with the negation, and so it's not like an extra instruction. It may look like, but it's usually not an extra instruction to perform, so you don't really lose anything on this, and while you have one less operator to implement, right? And the 3-way compare pre-C++20, how you could do that? Well, simply by just writing the function, right, that returns int. C already got it. You had this mem compare, there is a string compare. The C inherited qsort expects a function that returns an int determining the exact order, unlike C++, which introduced the concept of using only less than operation. C got it earlier, and so you enter your compare function, and I have first implemented it for the uint 16 so that it works in our point that used them, to showcase how it would work like. Then in our point, I am skipping the fixed part of the point to save on slide space. Then in our point class, we define the friend compare function that does it member-wise. First it compares the x, then it compares the y. And this, what you are looking here at, is almost precisely what the generated spaceship operator would do. It would compute the member-wise result and compare it to 0. If the result is not 0, then we already know the order. If it's 0, we continue with the next member. So the generated 3-way comparison, it looks the same. And then we can define all the operators. To simplify, I will use a controversial example of using preprocessor. I think this is a justified use of preprocessor. Note that the symbol is undefined immediately after its use ends, so it doesn't clutter the namespace. So here we again do exactly the same as with the spaceship operator. The compare result, we compare the compare result to 0, and the relation must hold. So if the compare returns 0, equals to 0, then the objects are equal. If it's less than 0, then the left object is less than the right object. So the operator here is exactly the same as the operator between the points compared. So this avoids some of the boilerplate code with this make macro. But of course, you can also write it by hand, repeating it many times. Now, the disadvantage of this approach is, of course, that to have full coverage, you have to write this version for every built-in type, like I did for the uint 16. and for possibly also for library types, right? And so because it assumes, here we assume that the members can compare this way. So to really support this, you have to cover all the types, and that's not as cool as it might be. And the last point is the use of tuple for dry. Don't repeat yourself. I have seen this trick in some code bases, and because it's pretty neat when you write it, but it has some consequences. So to our point member, we might add the tie function, which ties all of its members. And then we define the operator using the tuple, right? Because the tie returns a tuple, and the tuple has operators defined, which are of course done member-wise, which will be here our member-wise. And so I'm showing here only the quality operator, but this applies to all operators. You can define all operators the same way. Just propagate the same operator to the tuple made up by joining the members. And the advantage of this approach is that the operators are actually they are fixed. Like you could even again make a macro to define all of them, and only the tie method is the one which requires your maintenance. So you list the members only once, only in this one function. Whenever you add a member or you remove a member, you have to add it there. You don't have to modify all the operators correspondingly. So that's very convenient. However, there are disadvantages. The main disadvantage is the compilation time. If you compare the version using the tuple and the version that would do the direct comparison member-wise, well, the compilation time is, well, not so cool. While it may not matter for your project, especially a small project or a project which where the build time is not a problem, then the holding to the dry rule may be worth the case because it's easier to maintain. But if you have a huge code base and if your teammates have to wait minutes for a build to finish, then maybe using tuples all over the place is not a good idea. So in bigger projects, I would disadvise this approach. And anyway, well, the spaceship operator resolves this also. And to be fair, that's not just the use of tuple. The header itself adds most of the effort. And this is pretty important because this shows that just including the tuple header takes down the compilation time a lot. So if you have you keep including it in your core headers that are included in everywhere else, you may be paying a high price in the compilation time. So on the other hand, maybe you are dealing with an external library that includes the tuple for you, so you have no choice. You already have it there. Then perhaps using the dry rule is worth the case because the addition cost by actually using the tuple once you already included it is not that big anymore. So if you already had to pay the price for other reasons, it may be worth using it. And finally, some references. I encourage you to look through the first ones are the other lectures from other conferences. They go into detail with operator overloading and spaceship, how it works and what are the nasty details there. So if that was what you are missing or looking for, go there. They cover the topic in much detail and a longer time. And here we are focused mostly on the aspects that are not well covered. And also consider this talk to be a call for action, because obviously we might have someone fix the compiler to generate a far better code than it does now. It shouldn't be that difficult, I guess, but I have never submitted any fixes to compilers. So that's all for me. Are there any questions? There is a question there up. So just say it loud so I can hear it and I will repeat it.
where you would implement other comparisons on behalf of spaceship operator, like implementing spaceship operator, for instance, as a private member, and implementing other operators based on the optimized spaceship operator.
So to phrase the part that was without the microphone, you said that the spaceship operator may be suboptimal because it in the end computes a bigger result than each individual operator computes. It is more difficult to say the exact result than to only say that this condition passes or not, and whether it makes sense to make it private and define the specific operators in terms of explicit call to spaceship operator, right?
Yes, my main concern was with the clean code part, because whenever we use spaceship operator, we need to additionally compare the result to 0.
And I would say that it's better to dig into the generated assembly. It is often misleading to just look at the source code where you look the comparison to 0, but in the assembly it often is eliminated because the jump or compare instructions already compute this result. This goes the same with the bool. Somewhat it might be tempting to think that if you make an if statement on a bool variable, then it's somehow shorter code than making it on a relation expression between two integers. While that's not the case, in most cases, it will end up with the same assembly generated because the assembly instructions are somewhat different. They do some results anyway, and so where it textually the source may look more complex because there is this extra comparison, it doesn't show up in the assembly. But that's also as often with the optimizations and the generated code, it's case by case often, sadly.
So could it be possible that if we define a well-optimized spaceship operator, for instance, for some big data structure, and then we define the equal operator just as a call to spaceship operator with the right comparison to 0, would it be as optimal as just calling the spaceship operator?
I would expect so. Assuming the spaceship operator cannot be the quality cannot be short circuit on anything and do better than general spaceship operator. Assuming the spaceship operator is the best you can get for any comparison, then implementing other operators as a call to spaceship operator to get the numeric result and comparing it to 0. My understanding so far is that this does not add any overhead. But again, well, the results may vary depending on what the compiler generates. In particular, if you are not generating optimized builds, the compiler might actually want to generate the extra function, extra call, extra comparison for the debuggability. And then you pay the price. But if we talk about performance, I presume we talk about optimized builds, right? Because otherwise it makes no sense. And in that case, I would expect that this does not add any overhead. I didn't find any case where it would, but then again, I cannot prove it.
We have to conclude slowly, so maybe last quick question, if we have it. If not, okay. Adam, thank you very much.